Hi, this is Andrew again, CTR08108, Civil Engineering Principles and Materials 2. This is the fourth lecture, today we're looking at material variability, sampling, and also test method 1 from BSEN 408. I'll just pop over to our presentation slides. So engineering materials are inherently variable. For example, steel properties vary depending upon the chemical composition and methods of manufacture. Just put my little laser pointer on. Concrete properties change depending upon the amount of cement, type of aggregate, air content, and so forth. And obviously method of curing as well. Wood properties vary depending upon tree species, method of cutting, moisture content, and a whole lot more. Variability is an important parameter in defining the quality of civil engineering materials. The goal of this test program is also to assess such variability for a given material property in order to ensure it is within acceptable limits, usually proposed by a standard. In other words, material testings are performed not only to evaluate the certain properties, but also to assess how much variation of this property occurs within the entire batch of material. How do we assess variability? Using a bit of statistical analysis. Let's assume a sawmill wants to sell a stack of timber beams for structural use. In order to do such, a stack of timber must be certified for structural use. It must be checked that its variability of the certain property, let's say strength in this scenario, is within the limit imposed by the standards required. A measurement of variability is the standard deviation. You'll have seen this before, I'm sure. How do we assess variability? First, we assess the strength of each beam separately. So there's 22 beams in this data set, N being 22, and the Fi is a measure of strength, and I is the number for each beam. So you can see it's a pretty nice set. Some stronger than others, and some a bit weaker than others. And then to calculate the average, fairly straightforward. Sum of Fi divided by N. And we get the average. We can draw that on the graph. And then we get what's called a variance. So this is where each individual test, how that differs to the average. And so the variance is actually the average of the squared differences from the average value. So there's the equation there for what we call variance. And then to get the standard deviation, it's just the square root of the variance. Nice and simple. The standard deviation has the same unit of measure as the data itself. In this case, it's newtons per millimeter square. It gives a measure of the amount of variation of the material property, i.e. strength in this case, within a set of values. A small standard deviation means a small variation of the material property, hence a higher standard quality of the material being assessed. So on that note, when we look at these two samples here, we've got both sample sets have the same average value, 15.2 newtons per millimeter square. However, the standard deviation is wildly different. On the first set, we can see that it's 2.239. In the second set, there's 11.14. Again, looking at the graphs, we can see how that looks pictorially. that a lot of the material is in and around that average value, where on the bottom set you've got some timbers that are significantly stronger. That's a 38 units per millimeter square as opposed to 20. That's significantly better. So is that one, so is that one. But there's also some that are significantly worse. Like down here, for example, say like 2 newtons per millimeter square. And so in that, by saying the higher the average, the higher the standard deviation, the better quality of the overall stack. Okay. Sampling. It's not often or even practical that we can test each board within a set. Nonetheless, by testing a sufficient large amount of samples, it is possible to estimate with a sufficient degree of accuracy the properties of the entire lot. In order for the samples to be valid, they must be randomly selected. The sample must be representative of the entire lot, i.e. the differences and the variations occurring within the lot of the material must be present within the randomly selected samples. So you're not going out picking just the best ones, you want to pick a random selection and then just double check that that random selection is a good representation of the full stack. If the material property is estimated from a sample set, the reflection of the estimated standard deviation becomes what we saw before, the variance and the standard deviation. So we're now going to look at BSEN 408. Do I have that open? I think I do actually. Let's have a look. Pause just now. So yes, BSEN 408. I have that here. This is the document. It's actually on Moodle for you. You'll find that on the Moodle page. And we'll come back to that in a minute or two. The example test carried out during this practical sessions will be based on this standard. You will need to read it and understand the test procedure, the analysis of the data, and how to write your report. For this first coursework, you'll be looking at material properties assessed by modulus of elasticity and material strength. Go back to that document for a second. Just for coursework 1, you'll want to have a look at page 20. Starts here, section 14, and you'll want to read down. And then you'll also want to read, I think it's page 32, if memory serves me correct. Yes, page 32. This is the format for your report, your test report. Everything that it says here, I would literally copy and paste that into a blank Word document and use that as your template for your report. Again, we'll go over that in class, or we have went over that in class. Let's go back to the slides. Right. As we will see, timber is not isotropic material, meaning that the strength, material stiffness, elastic modulus, differs according to the direction that they are measured. In this sample here, the direction of the grain is going horizontal. We determine the following strength properties. F, compressive strength parallel to grain, denoted by FC0. C meaning compressive, and 0 is the angle to grain, which means 0 degrees to the grain, I suppose. And then the tensile would be pulling it apart in that direction. compressive strength orthogonal to the grain or perpendicular to the grain, FC90. 90 is just the direction to that grain, and it's obviously in compression. We've got the tensile equivalent perpendicular to the grain. Question, ask yourself this, how many different directions orthogonal to the grain are there? Right, have you got your answer in your head? Well, actually, it's infinity. Every direction, timber is timber. Timber is a natural material and it's not going to behave in a uniform manner. Okay, with that said, as for the strength properties, we will have the following material stiffness. It's the stiffness properties, which is the MOE, or modulus of elasticity, or Young's modulus. Elastic modulus in compression parallel to grain, EC0. We can get that from this test that we'll be doing. Then we've got the tensile modulus with the grain. We've got elastic modulus in compression orthogonal to grain, so it's EC90, and then T90 for tensile, pulling it apart. During our last experiments, during the practical session, we will only be concentrating on deriving the following properties, which are compressive strength parallel to grain, compressive strength orthogonal to grain, modulus of elasticity parallel to grain, and then perpendicular to grain. And then also we'll be looking at the bending strength, but we'll talk about bending strength another time. So if we're to go back to that document that we had before, BSEN 408, look at page 22, we will get the determination of compressive strength parallel to grain. Pull it up just now, page 21. There we are. Clause 15.2, the test piece shall have a length of 6 times the smaller cross-sectional dimension. So L equals 6 times B. Clause 15.3, pardon me, the compressive strength is given by this equation. FC0 equals F max divided by BH. BH is just the area, and F max is the highest value within the entire curve. So just you find the F max there. Perfect. Now we want to calculate the modulus of elasticity parallel to grain, or EC0. Again, from the same page, page 21. We'll find it in section 14.1, 2, and 3. Again, it's actually the same sample, it's the same test, same data. Again, L equals 6 times B, or H, whatever's smallest. And the expression is going to be this expression here. EC0 equals L multiplied by F2 minus F1, all divided by the area, or BH, divided by BH, multiplied by W2, take away W1. Okay, that sounds okay. However, what are F1 and F2? What are they? F1 and F2, for a starting point, what we'll do is we'll take F max and we'll take 10% of F max to get F1, and then we'll take 40% of Fmax to get F2. Then the corresponding data to that will give you W1, W2, or that movement in millimeters. Now, we're using the word approximately here. There is a caveat to how good a fit that actually is to the data. So we can see here it says, such that the straight line connecting the 2 points overlap as much as possible with the experimental curve. Now what that means is, there is within the document BSEN408, this document here which we showed you before, within this document here, there is a caveat to where that overlap as much as possible is acceptable or not. You'll have to find out what that is and how to make sure that it is or it is not acceptable. If it's not acceptable, well, what that will generally mean is that the data is not fitting well, and it could be if it's not fitting well at the bottom, which it usually would be the bottom, you could just move F1 up a little bit to make sure that the section between the 2 points are fitting a little bit better. We can go over this in class if need be. Any questions, do ask. But again, it's all written within BSEN 408, and you're allowed to move that. You're allowed to move both these points such that the data is more precise. Where this expression actually comes from. Now again, we've got the behaviour of E. E, modulus of elasticity, is stress over strain. And stress is just force over area. So force over area. And then strain, is delta over L. Delta over the original length. So when you write all that down, this is exactly where this expression comes from. The reason why we do not consider this small section here of that curve is mainly because as you put the timber into the machine and you start the compressive test, the timber wants to settle a little bit. Maybe it's not cut perpendicular and it's not perfectly cut. So you will have a little bit of settlement as we start to put the load onto it. So that just takes out any of these anomalies. Okay, we're almost finished. Now remember, take plenty of photos during the lab session. Please make sure you do not miss the lab session because it's up to you to be there. And also what you'll want to do is you'll want to go to that document. Where's that document? Here. You can read through how the test procedure is meant to be carried out, then go back down to page 32. Read through this thoroughly and make sure that you've got some questions to ask the lab technician about anything that's written in this document. You'll have to, this is your template for your report. So it might be, an example would be conditioning of the sample or the region of where the sample came from. Read through this report. Anything you don't understand, when you're at the lab session, that's your time to ask. Ask the question. Do me a favour as well. Ask your questions out loud so the whole class can hear. And so when the technician then responds, you then all can get the same answer from the technician. Go back to our sessions. At the completion of each test, you will have a text file on a comma delimited file actually, listing all of the points making up the load displacement curve. You need to put this into Microsoft Excel, generate your graphs, and then calculate your findings as such. We will be going over this in our tutorial sessions using Microsoft Excel, so please go and attend all of those if you can. Oh, sorry, go back to where we are. If you don't know how to use Microsoft Excel to do this sort of thing, these two videos may be of help, but I would strongly suggest you come to our tutorial sessions. Okay. Now, as I said, this is only just a snapshot or a summary of what's said in class. It's up to you to be in class, but if you can't make it for some reason, this is what these videos are for. Right, thank you very much. Best of luck.